If you're enjoying Why This Universe, there's another University of Chicago podcast network show that you should check out, and it's called Big Brains. Big Brains brings you the engaging stories behind the pioneering research reshaping our world. Change how you see the world and keep up with the latest academic thinking with Big Brains, part of the University of Chicago podcast network. So one of the things that cosmologists are most interested in studying is what the universe looked like in its very earliest moments, like right after the Big Bang happened. And we can get pretty close. With experiments like the Large Hadron Collider, we are actually testing what the laws of physics would have looked like up to a trillionth of a second after the Big Bang. And this is just some really phenomenal experimental work, but what about the time that we don't know about? From time equals 0 to time equals 1 trillionth of a second, for example. That period of cosmic history may have been short, but there's a chance that it had a tremendous impact on what the universe looks like today. In today's episode of Why This Universe, we'll talk about a very popular idea for what could have been going on in that time, the theory of inflation. And if it's true, it means that the universe once behaved unlike anything we've ever witnessed, and it might even imply the existence of a new kind of multiverse. You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. My name is Shalma, and I'm a PhD student at NYU.
And I'm Dan Hooper. I'm a theoretical astrophysicist at Fermilab and at the University of Chicago.
So to understand the motivation for the theory of inflation, we have to talk about the Big Bang Theory. The Big Bang Theory tells us that the universe started out in a state of infinite density and then expanded outwards over time. It turns out that while this theory is very well accepted today, it does leave us with some unanswered questions.
So in the original version of the Big Bang Theory, the kind that was kind of coming into fashion or becoming popular in the 1960s and 70s, the universe had just expanded in a smooth, steady way over its entire history. It was expanding faster in the past, but still in a smooth, slowing way across all 13.8 billion years of cosmic history. But it turns out that this version of the Big Bang Theory had some problems that started to become apparent. I think in the 1970s, they started to worry people in a real substantial way. The first of these problems is called the Flatness Problem. So the idea here is that for a given expansion rate at a given moment of time, the geometry or shape of the universe depends on how much energy is in space. So if you have a really high energy density, space will be positively curved. If you have a low energy density, it will be negatively curved. And what I mean by that is things like parallel lines either converge or diverge from one another, depending on if space is positively or negatively curved. And things like the angles of a triangle add up to either more or less than 180 degrees, depending on if space is positively or negatively curved. If you had exactly the right amount of energy in space, you could have a totally uncurved space, a totally flat space, or Euclidean space. But no one expected this to be the real outcome. After all, exact flatness would be very, very precise and specific, and there was nothing we knew about the universe to lead us to expect that to be the very specific case. It's kind of like if you took a wheel and you just spun it on its axis or something, and when it stopped, it was pointing exactly in the direction of north, like to many, many significant figures of in degrees or something. I guess it's logically possible that could happen, but you would never expect that to happen, by chance.
Just like super coincidental.
Super coincidental. It would probably require some sort of explanation if you found it that way. So, but in the 1970s, cosmologists started to kind of measure the energy density and expansion rate of the universe, and it looked like our universe was very roughly flat or Euclidean. So it's like that wheel is pointing northward, and we kind of thought you needed an explanation for that. One thing that makes this even worse is that as the universe expands, it tends to get more curved as time goes on. If it's positively curved, it gets more strongly positively curved. If it's negatively curved, it gets more strongly negatively curved. So to find our universe in a state today that's approximately flat means that in the early universe after the Big Bang, it must have been flat to about 1 part in 10 to the 60, which is incredibly coincidental. And this has only gotten worse as we've measured these things better. In the 70s, we knew the energy density of the universe to maybe an order of magnitude. Today, we know it to a fraction of a percent, and it really looks like our universe is very close to flat. So the second problem that cosmologists were dealing with when it came to the Big Bang Theory in the 70s was something we call the horizon problem. So an empirical fact, an observational fact, is that our universe is remarkably uniform. So, for example, if you look at the light that was created with the formation of the first atoms a few 100,000 years after the Big Bang, we call this a cosmic microwave background.
We also call this the CMB for short.
The temperature of this light is basically the same in all directions. It's about 2.7255 degrees above absolute zero. The hottest and coldest parts of the cosmic microwave background are hotter and colder only by about 1 part in 100,000. So it's really this remarkably uniform background of radiation. And that tells us that the energy density of our universe was really uniform a few 100,000 years after the Big Bang. But this raises a pretty big conundrum. After all, how did all of these parts of the universe come to be so uniform? How did they come to be synchronized? If you found a bunch of stopwatches that were all, reading exactly the same time down to the millisecond, you would assume some mechanism arranged for that. But when we look at the CMB, we're looking at different parts of our universe from a long time ago, and those parts were not in causal contact with each other. They had never been in contact. Even traveling at the speed of light, they couldn't influence each other. So there was no explanation for how they came to be so synchronized, so uniform. It called out for some sort of explanation, but in the context of the original Big Bang Theory, there just wasn't any good explanation forthcoming.
So if these parts of space were once in causal contact, like if they were all much closer to each other and could exchange heat, then it would make a lot of sense for them to all have the same temperature. After all, if you put a hot thing next to a cold thing, they will exchange heat until they arrive at some same medium temperature. But as it stands, these parts of space are so far away from each other that it seems impossible that they could have ever causally impacted each other. In other words, they're so far away from each other that light could never travel between the 2 points within the history of the universe. So, if they couldn't actually exchange heat, then how is it possible that all of these points in space ended up at the same temperature?
All right, so the third problem that cosmologists were worried about in the 70s when it came to the Big Bang Theory has to do with something called magnetic monopoles. So grand unified theories were becoming really popular in the 70s, and most of these theories predicted the existence of these weird exotic objects called magnetic monopoles. So if you find a magnet in nature, it always has a north and a south pole, like a picture of a bar magnet or something. You never find a north pole without a south pole or vice versa. This turns out to be the same thing as saying that although there's electric charge, things with electric charge in our universe, there's nothing that carries a net amount of magnetic charge. At least we've never seen anything like that. But in these grand unified theories, those things should exist. There should be magnetically charged objects. We call them magnetic monopoles. And it turns out these particles or these objects are not really particles, but these objects should be really, really heavy. And in the very hot Big Bang, they should have been produced in huge quantities. And they should be all over in our universe today. And they should be very easy to detect, but we don't. So the problem is, if all these monopoles were created in the early universe, why don't we see them everywhere we look today?
So basically, a magnetic monopole would be a magnet with only one pole, like only a north pole or only a south pole. If you took a normal magnet and broke it in half, you'd still get 2 smaller pieces, each with both a north and south pole. But according to our best theories of physics, it seems like these magnets with only one pole should exist, even though we've never seen them. So that's the third problem that was left unanswered by the Big Bang Theory alone.
So all three of these problems were kind of, being thrown around in the 70s, the flatness problem, horizon problem, monopole problem. I don't think most cosmologists were like deeply worried about them, but it was in the water. People were talking about this sort of thing.
Was it obvious that these three problems were related to each other?
I don't think so. So I'm not sure that it was obvious they were real problems, first of all. Some people thought they were worried about them, others maybe less so. I don't think it's super obvious that they would all have a common solution. But that common solution came from a guy who wasn't even a cosmologist at all. He was a particle theorist at the time, a guy named Alan Guth. He was a postdoc, and at that point he wasn't famous or anything, but he would become famous for this idea. And basically what he proposed is that maybe in the very early universe, there was a very brief period of very, very fast expansion of space. So this, it turns out, if you posit this era of hyperfast expansion, what we now call cosmic inflation, you can solve all three of these problems all at once. When you inflate a piece of space at a quick enough rate, it tends to make it flatter as it expands. So this is kind of like if you take a balloon and you literally blow air into it. If you take a patch of that balloon's surface, it looks like it becomes flatter as it gets more air in it. So you can solve the flatness problem that way. You can also explain the horizon problem, the uniformity of our universe, in other words, that problem, because different parts of that balloon were once really close to each other. They were in contact with each other so that they could kind of take on the same energy density. And then they get blown apart in this hyper fast expansion, and they look like they're causally disconnected, but in fact, they used to be connected to each other. So you can solve that problem. And then the monopole problem you can solve really easily too. After all, you might make a ton of these magnetic monopoles, and then the volume of space grows by a huge factor, diluting their abundance so that we shouldn't be surprised that we haven't seen any in our universe today. So you can kind of kill three birds with one stone with Guth's idea. But to do this, inflation has to be pretty dramatic. This isn't a subtle effect. Modern versions of inflation have the volume of any patch of space growing by a power of 10 to the 75, a factor of 10 to the 75, in something like 10 to the minus 32 seconds. I'm just going to repeat those numbers because they're gargantuan, right? 10 to the 75 times is how much the volume increases by in a time span of 10 to the minus 32 seconds. So truly dramatic. It is not, inflation is not a subtle effect. It is a catastrophic, space, destroying, universe transforming era of cosmic history.
I'm sure someone is going to ask, how could this be faster than the speed of light? But it can.
Yeah, so everyone learns that nothing can move faster than light, but the real rule, according to relativity, is that objects can't move through space faster than light. Space can move at any rate it wants to. Space itself isn't, held to any speed limit by relativity or anything else we know about the laws of physics.
Right. So in inflation, space itself expanded much, much faster than the speed of light.
Very much so, yeah. If you had 2 points in space that were separated by the diameter of an atom or something, by the time inflation was over, or even actually much before that, they would be totally separate in different universes for all intents and purposes, totally causally disconnected. Space tore everything apart from everything else, making the universe cold and empty almost instantaneously. So this raises an important question, obviously. So, if we want to posit some sort of dramatic event like cosmic inflation, we have to ask, well, what could cause this to happen? So to kind of understand this, I think we should go back to Einstein's general theory of relativity, and think about what those equations say space-time should do in the presence of matter or energy in it. So to do this, we use something called the Friedmann equation, and it tells us that the rate at which space expands is proportional to the square root of the energy density it contains. So our universe today is pretty cold and empty. It doesn't have a lot of stuff in it, so it's expanding at a pretty modest rate. That rate is about 70 kilometers per second for every megaparsec separating 2 points in space. So a megaparsec is about 3 million light years. So if you take two different points in space, 3 million light years apart from each other, those 2 points in space will be moving away from each other at about 70 kilometers a second. As an aside, there's a big controversy going on in cosmology right now. People are arguing very fervently that this rate of expansion is like 73 kilometers per second per megaparsec, and other people are arguing equally fervently that it's 67 kilometers per second per megaparsec. I once in a cosmology class asked the class if they knew what the rate of expansion was. One of the students asked if I was trying to start a fight by simply asking that question. It's a very hot topic. But anyway, that aside, it's about 70, plus or minus a few. So if we go back farther in cosmic history, the universe was smaller and more dense. So the Freeman equation says that space should have been expanding faster. For example, if we go to a point about 200 million years after the Big Bang, this was like when the first stars were forming, the energy density was about 1,000 times bigger than it is today. And that means that the expansion rate was about a square root of 1,000 or 32 or something times faster than it is today. And if you go back even further, it was faster and faster and faster. If you went to the 10 trillionth of a second after the Big Bang, where the LHC measures, the distance between any 2 points in space was, doubling every trillionth of a second or so. So it was very, very fast, very early on. But even that sort of rate of expansion is really nothing compared to what we're talking about with inflation. And to explain this, we need kinds of energy that you can put into space that aren't like the normal forms of energy we see in our universe today. So we see things like dark matter, we see things like atoms, we see things like light. None of this stuff can make the universe expand at the kind of exponential rate that you need to explain inflation. Instead, you need to posit some sort of like vacuum energy or energy density of space that doesn't dilute as space gets bigger. This could go back to Einstein's notion of a cosmological constant. It might be related to what we call dark energy in the universe today. Frankly, we just don't know. But in order for something like inflation to have taken off, there had to have been an era where the universe's energy was mostly made of this vacuum energy that just didn't go down in its density as the universe got bigger.
So inflation would have started because of some vacuum energy of empty space, something like what Einstein described with his cosmological constant, or like dark energy. But if this vacuum energy doesn't decrease as space expands, then why would inflation ever stop? Why wouldn't the universe just keep expanding at this huge exponential rate, making the development of stars and galaxies and ultimately us impossible?
So in Alan Guth's original proposal for inflation, it was really challenging to figure out how this era might have come to an end. I mean, inflation kind of just should have gone on forever. And Guth basically posited that there might have been some big spontaneous transition from this inflating state to a normal state. But this left the universe kind of empty without any matter or energy in it. And this does not look like the Big Bang as we know it. So that can't be the real answer. But shortly thereafter, a bunch of other people kind of picked up the ball where Guth had left it, people like Andre Linde, Andy Albrecht, Paul Steinhardt, and others. And they had these new ideas for how inflation might have come to an end, where that vacuum energy, where that energy of the cosmological constant that was driving inflation could be converted into things like hot particles that could fill the universe, basically setting it off in the sort of Big Bang that we know and love. So this is a good theoretical idea. It can solve, the flatness problem, the horizon problem, the monopole problem. But from what I've told you so far, I wouldn't say there's a convincing reason to think it actually happened. Just because something can solve some hypothetical problems doesn't mean it's the right solution. But it turns out that inflation, as it was posited back in the 80s, makes some fairly specific predictions, and those predictions have, for the most part, panned out pretty well. In particular, in the inflationary theories that were being talked about as early as the 1980s, they said that the density variations in the early universe should have had two very specific features. They should have been what we call adiabatic and nearly scale invariant. So let me unpack what those things mean. For them to be adiabatic means that the distributions of ordinary matter, dark matter, and radiation in the early universe all should have traced each other. In the parts of the universe with more dark matter, you'd also find more atoms and more radiation. And in places with less dark matter, you'd also find less atoms and less radiation. That turns out to be true, the best of our ability to measure it. And when it comes to scale invariance, what I mean by that is that our universe should look approximately, but not exactly like a fractal. If you take a mathematical thing called a fractal, you zoom in on it, you find the same sort of images as when you zoom out. So you zoom in, you zoom in, you zoom in, and each layer looks like the thing you had previously seen. So our universe in its primordial state looked pretty fractal-like. It had a little bit of a tilt to it, but basically it was approximately scale invariant, just like the original versions of inflation predicted.
So to be clear, when we're talking about our universe as a fractal, we really are talking about this early, what we call primordial stage of the universe. Eventually, gravity kicks in and starts clumping things up in atoms and molecules and galaxies, so the universe no longer has this fractal-like property of scale invariance. So if you zoom into an atom today, you won't see the structure of the entire universe or anything like that.
So in the modern measurements of the cosmic microwave background, we find our universe is highly adiabatic and nearly scale invariant. And I would say that it's in 2021, most cosmologists are pretty convinced that inflation or something very much like it took place in our early universe. There are, prominent naysayers and opponents to this idea, but, it's definitely the leading hypothesis for our very early universe. And the people who are arguing against it are definitely in a distinct minority.
So the fact that inflation made these successful predictions means that people take this theory very seriously today. But what does the future look like in our studies of inflation? Could we ever really confirm that inflation happened?
So going forward, cosmologists have a lot of ideas for ways that they could test different theories of inflation, maybe confirm that it really took place, and better yet, teach us things about, how and why it played out the way it did. One of these is that as inflation was coming to an end, a lot of gravitational waves should have been released into the universe. These are like ripples of space and time that travel through space, are predicted by general relativity. And these should lead to very specific features in the cosmic microwave background that we call B-mode polarization. So far, we haven't observed this, or at least any kind of primordial B-modes. But we have a lot of experiments in the planning stages that could be sensitive to these sorts of signals. That's the sort of thing we could do to learn about inflation and like maybe when in early cosmic history it might have taken place. Even better, we have ideas for deploying space-based gravitational wave detectors like LISA. It's the name of a prominent idea that might be able to detect gravitational waves from the early universe. It's not a sure thing, but if that were to happen, we could learn a ton about inflation and other aspects of our very, very early universe's history from the gravitational wave signatures they produce. All right, and then there's one last thing about inflation, which personally is my very favorite thing about inflation. And that's that once inflation starts in a patch of space, it seems like it shouldn't ever stop. It should just keep going on forever. So let me give you kind of an example. Let's say inflation goes on for like 10 to the minus 33 seconds in some piece of space. And in that 10 to the minus 33 seconds, there's like a 10% chance that any given patch of space will stop inflating and kind of get reheated and form a normal universe as we would know it. But not all of the space stops inflating at that step. 90% of it just keeps going on. And then it goes on for another 10 to the minus 33 seconds, and it grows in volume by a factor of 10. And again, 10% of that new volume stops inflating, making some new patches of hot universe. And then this just keeps going on, making universes without limit. The volume of inflating space never goes down. It only increases. And that means this should really go on forever, making a very large, if not infinite, number of universes. So in this sense, inflation seems like it should be eternal and really never come to an end. And that means that our universe is very likely just one of a very large number that inhabit a greater multiverse that comes out of the idea of inflation.
I think this idea is just so cool. It's a theory of the multiverse where all of the different universes exist on the same plane of space-time, but each universe is just completely causally disconnected from all the other universes because of this huge distance that space has expanded between them.
I mean, there are a lot of different kinds of multiverses physicists talk about. The inflationary one is like one of the more well-motivated, in my opinion. I should just add that like some of these patches of space might have the same sort of laws of physics that ours do, or similar features overall, and others might look and seem, behave very differently. So it really is a playground for a theoretical physicist to imagine what the greater multiverse might look like or behave like.
So while we can never go into these other universes and learn about them directly, it could be that by learning more about the theory of inflation, we could learn more about the prediction of this kind of multiverse.
So it's kind of on this boundary of empirical and purely speculative physics.
This episode was produced and edited by me, Shalma Wegsman. Research and writing is done by Dan Hooper and I. Dan is a theoretical physicist at Fermilab and the University of Chicago and is the author of many books, including most recently, At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. All music in Why This Universe is produced by Jake Kleinbaum. Thank you so much for your support and for listening, and we hope you tune in next time to Why This Universe.